Okay, so now that we know about these viscous forces, these kind of internal frictional forces that act between kind of like different layers of molecules within a fluid that try to oppose the relative motion of these different layers of molecules, let's talk about some of the simplest types of flows. In this case, let's start out in section 7.2.1, with flow through a straight pipe. Flow through a straight pipe. Okay, so, to make life easy, let's suppose we just have a horizontal pipe with water flowing through it. Water is coming in here, it's going out here. I'm just looking at like some internal cross-sectional chunk of it. And to make life easy, let's suppose, there's no gravitational forces that we need to worry about. There's just some, high pressure pump or something on the left side here, making the water flow to a lower pressure region over on the right. Okay. So because there are these internal viscous forces, even when water is flowing smoothly and nicely through a straight pipe and nothing interesting is happening, even in this case, the fluid doesn't actually flow at the same velocity everywhere within the kind of cross-sectional view of this pipe. Right? So what actually happens, at the very edges of the pipe, again, there are often these kind of weak chemical attractions between the layer of molecules right next to the pipe and the pipe itself. And these molecules like barely move at all. So, they would have like a very small velocity in this direction. So they're barely moving. The layer of molecules just above them, is trying to move faster because of these pressure differences. But the viscous forces from this almost motionless layer are acting to slow them down a little bit. So the next layer, moves faster, but, still not, it's still slowed down by these viscous forces, and so on and so forth. The next layer of water is able to move a little bit faster, but there's relative motion of this layer with this slower layer below it. That tends to slow it down. And so what you end up with is this kind of profile of velocities, where water in the very center of the pipe is actually moving faster than the water in the layers just next to it, like a concentric shell of layers next to it. Those are moving faster than the shell around it, so on and so forth, until you get back to the walls of the pipe, and the water is really barely moving because of these kind of weak chemical attractions with the pipe. So because of all of these viscous forces, instead of just flowing freely, water requires a consistent gradient in pressure, consistent gradients in force across their cross-sectional area in order to keep water moving along the pipe, right? And so just like doing work, let's say, against the force of friction when we're sliding, a bookcase across the ground, we're having to do work, and some of that work gets, wasted going into frictional heating, or in this case, what you might call viscous heating. So even if we don't always notice it, flowing water heats up in the same way that two solid surfaces rubbing against each other heats up, because you have these layers of molecules sliding against each other. Okay, so the first thing that we learn is that even if you're just simply, smoothly flowing through the most boring, pipe or hose, perfectly straight, no gravity, even in that case, there's this interesting change in how fast different layers of the water are actually moving as you go from the edge of the pipe to the center. Right? Because there are these viscous forces, some of the work that you're doing to pump this water is actually just going into viscous heating the fluid up. Okay. Now, there's an important difference between viscous friction and ordinary sliding friction of two solid surfaces against each other. And that's something that we said back in chapter something or other, which is that, for sliding friction, the magnitude of the friction force doesn't really depend very much on how fast the objects are moving. It's just if there's any relative motion, then you have this sliding friction. Okay. Viscous forces really do depend on the velocities of these different fluid layers, right? And so as the relative motion within a fluid gets larger and larger, the viscous forces get more and more important. Okay. Now, you might wonder, suppose I have, this kind of flow through a straight pipe. there are these strange velocity profiles of flow in different layers of the water. I'm imposing some pressure gradient with a water pump or something in order to get the water to flow. You might wonder, like, how much water is actually coming out of the end of this pipe, for instance. So the way that water flows through these straight pipes or hoses can be summarized by something called Poiseuille's law. And I know neither offhand how to pronounce this or really how to spell it, so I have to constantly look. Poiseuille's law is a way of combining all the things that we know are important to fluid flow. Like, we know there's some amount of pressure difference, we know there's some viscosity, we know these pipes have a certain size. How much water do we expect to flow out of this pipe? Poiseuille's law summarizes all of that for us. So first, let me write the equation down, and then we'll go through it piece by piece. So first, I have a change in volume in a certain change in time. That's going to be equal to some numbers, pi divided by 128, times the change in pressure divided by the length of a pipe that we're interested in, times the diameter of the pipe to the fourth power divided by the viscosity. Okay, so let's go through this equation, which is trying to tell us how fast does water flow out of a pipe, or flow through a pipe in total, piece by piece. So this first part is, we can think of as kind of like a flow rate. So it's like, imagine I have, because this is where my picture is going to be. So imagine I have this pipe, and this is the end of the pipe, and there's just a certain amount of water gushing out here, right? So the flow rate, this change in volume per change in time, I can think of that as, suppose I have a bucket down here that's, collecting the water that's flowing out of this. This flow rate is like, how fast does this bucket of water fill up, right? How much volume of water do I add to this bucket in every amount of time? Okay, so that's the flow rate, and that's what Poiseuille's law is able to predict. Okay, these things, pi over 128, those are just numbers. To turn this into an equation, the scientist did a bunch of heavy math to figure out that the numbers that we needed were pi and 128. All of the rest of this you could have perhaps predicted by dimensional analysis, if that's something you want to think about. But pi over 128, that's something you need to actually do math to figure out. Okay, now we have these kind of four other pieces. We have a change in pressure, we have a length of a pipe, we have a diameter of a pipe to the fourth power, and we have this viscosity. Let's kind of think about those each in turn. Okay. So the first thing is we have this delta P, this change in pressure, right? So what this equation tells us is that the flow rate is proportional to the pressure difference between the start and end of the pipe. That's what this kind of delta P means. Now, you might think that, this kind of makes sense, I would say. The pressure gradient determines how hard the water is being pushed. You might say if this end of the pipe is open to the air, that's at atmospheric pressure. So how hard we're pushing is like, well, how far above atmospheric pressure are we applying a pressure at the input end of the pipe? Okay, so the higher the pressure gradient, the greater the flow rate. I would say that makes sense. So higher pressure difference leads to higher flow rate. Nice. Okay, the next piece that I want to talk about, so I've got, I did this piece. Next, let's have this flow rate. Flow rate is inversely proportional to the length of the pipe. So actually, if you have the same pressure gradient, you've got a pump that's able to supply the same maximum pressure, and you just make like your garden hose longer and longer, the flow rate at the end of the garden hose will be less, and it will be less by like an amount inversely proportional to the length of the hose. The way that we should think about that is the longer the hose is, the more opportunities there are for these viscous forces to slow down the motion of the fluid through the pipe, right? So you might say more opportunities for viscous forces to oppose relative motions. Okay. The next thing that I want to talk about is that the flow rate is also inversely proportional to the viscosity. And again, the reason for that is, I think, as straightforward as it being inversely proportional to the flow rate itself. So flow rate is inversely proportional to the viscosity itself. Viscosity of the fluid. Again, I would say this makes sense. It's like viscosity is what's opposing this relative motion in the first place. So if you have the same pressure difference and you have the same length of pipe, and you're trying to flow water through it versus honey through it, well, the more viscous substance is going to flow a lot less well. And so flow rate inversely proportional to this viscosity. The last piece of this equation is this fourth power of the diameter. Flow rate is proportional to diameter to the power of 4. And intuitively, I think it makes sense that, if you have the same pressure difference, the same viscosity, the same length of pipe, then the, bigger you make the cross section of the pipe, the more flow you get. I think that makes sense. The fact that this is 4 powers of diameter, that might surprise you. So where is that coming from, right? So the idea here is that, first, this is two effects. So effect A is, if let's say I double the diameter, I quadruple the cross-sectional area. Right, so I have a circle, and now I make my circle twice the diameter. That multiplies the area of the circle by 4, right? And so that's quadrupling the amount of space that we have for fluid to occupy. Okay, so that gives me 2 of these 4 powers of the diameter. But the other effect is that the fluid at the center of the pipe can also travel 4 times as fast if I double it. So again, travels 4 times as fast if the diameter doubles. Now, that's the result of a calculation that I have not shown you because, the goal of this class is at some level to avoid some of the complicated calculations that go into a lot of these problems, but instead focus on the physical ideas. So, without doing that, you might not have a perfect idea of what is the shape of this, way that the velocity changes as you go from the edge of the pipe towards the center of the pipe. It turns out that the way this works is, flow rate at the center of the pipe grows like the square of the diameter of the pipe itself, okay? So that's maybe not obvious, but it gives you another one of these effects. So doubling the diameter quadruples the volume of space available for the fluid, and it also quadruples the speed of the fastest flowing parts of the fluid. You put those together, and you see that doubling the hose diameter, it's 4 powers, so doubling the hose diameter actually lets you flow 16 times as much fluid in the same amount of time for the same pressure difference, and if you have the viscosity the same and all that stuff. And I just want to dwell on that for a little bit, because diameter to the 4th power is actually a pretty strong effect. So it means, if you take a garden hose, for instance, and you make the diameter just 20% bigger, 1.2 to the power of 4 is basically a factor of 2, right? So what I'm saying here is if you have the same, say, amount of pressure that your house is able to supply through its water system, and you have a garden hose which is just 20% bigger in its diameter, right? So you make it go from a diameter of 1 inch to 1.2 inches. That doubles the amount of water that hose is going to pump out per unit time, right? That's a big effect on the scale of things. Okay, so this is what happens in the simplest possible scenario of a flowing liquid completely enclosed as it's going through a straight pipe. What happens if it's going not through a straight pipe, but through a bend? So this is section 7.2.2, dynamic pressure variations. Pressure variations, parentheses, I don't know, flow through a bent pipe. So one of the things that makes fluid flow complicated, and this is something that I talked about in the last recorded lecture, is that in addition to static variations in pressure, the kind that you can get by someone like squeezing on an enclosed bottle, or the fact that as you go deeper into a lake, say, the pressure gets deeper the deeper you go, gets higher the deeper you go, you can also get pressure variations just due to the motion of the fluid itself. So let's imagine that I have flow through a pipe that goes through a 90-degree bend. Okay, so I've got water that's kind of, flowing like this. Let me try to draw this slightly better. Right, so I've got water flowing towards this bend, and then, at the end of the day, it needs to be, getting back to what its steady state flow is at that straight section of the pipe. What happens as it goes around this bend? Well, as the water starts bending around, going through this turn, you can see that the velocity of the water has to change. It has to change from going straight to going, or let's say going straight up to going straight to the right. So even if the velocity of the water wasn't changing, we can see that there are accelerations involved here because the direction of the velocity, at the very least, has to change. So as the velocities change, there are pressure variations that go along with it, and this all actually gets kind of interesting and complicated. If you like, one way we can think about this is in terms of the centripetal accelerations we thought about in uniform circular motion earlier in this class. As I follow water, like around this bend, it's like rotating, as if it's going partly through some kind of circular motion. And water out here is also going through some circular motion, right? With maybe a circle which is effectively bigger than water tight in here, right? So because the direction of the water has to change, and we have these almost like centripetal accelerations of these layers, these streams of water, there's going to be gradients of pressure within this pipe. So it turns out that you end up with regions of high pressure at the outside of this bend, high pressure at the outside of the bend, and kind of relatively lower pressure on the inside of the bend. At the same time, we know that there are these effects where fluids try to accelerate, from regions of high pressure to regions of low pressure, right? Another way of thinking about this is, if I have water, that's coming this way and it's about to see a region of relatively lower pressure, actually not only is it going to be lower pressure, but also higher speed. Higher speed. And similarly, water that's approaching this region of higher pressure, well, it tries to accelerate away from these regions of higher pressure. So actually, as the water approaches here, it starts to slow down as it gets into this high pressure region. So in this bent pipe, we have regions of higher pressure and lower speed of what the water flow is looking like, right? So this is kind of what happens, just kind of in a cartoon picture, ignoring the details of precisely how much the velocities change and how much the pressures rise or lower. One way to kind of help remember this kind of back and forth between changing pressure and changing speed is to kind of invent a fictitious new type of potential energy, a pressure potential energy that works for fluid flows, right? And so just like, let's invent a fictitious pressure potential energy. And the reason that I think sometimes this helps kind of remember all of these effects is, again, think back to throwing, a apple up with some velocity. What happens? At first, the apple has kinetic energy, so it's moving at some velocity. As it rises, it exchanges some of that kinetic energy for gravitational potential energy. right? So gravity is always pointing down, acting on that apple. So its velocity gets less and less as it gets higher and higher, until eventually, at the peak of its trajectory, it's traded all of its velocity for gravitational potential energy, and then it starts trading that energy back, and gravitational energy gets put back into kinetic energy. Well, in the same way, the velocities of the fluid, these different layers or streams of fluid within the overall flow, can kind of trade their own kinetic energies, their own velocities, for this kind of pressure potential energy. And then when they go from high pressure potential energy, where they've lost some of their speed, back to kind of whatever the pressure is here, some lower pressure, they get some of that speed back. Right? Okay. So this is the simplest example of that I can think of anyway, of how you can encounter these dynamic variations in pressure within a fluid flow. So the flow of the fluid itself, just having to go through a turn, itself generates these changes in pressure within the fluid, and then that kind of feeds back into, well, what effects on the flow itself does this have? Okay. Now this all, both flow through this bent pipe or flow through this straight pipe, is kind of assuming that you have the smoothest possible type of flow. There's no eddies, there's no vortices, there's nothing complicated about the flow itself. You just have these nice smooth layers of fluid moving at different velocities. In the next section, we'll start to talk about the difference between these smooth flows and kind of more exciting, harder to understand, more fun turbulent flows.